So we're going to look at a couple of examples here. And first, let's go through each one of these compounds and, excuse me, let's pick out the non-equivalent protons. Let's do that. So what do you think about number one? How many signals is that going to generate?
4.
4 signals, good.
4. Yeah.
Saying these right here will give you a signal. Is that right?
Yes.
And then the ones here, that's going to be a different signal, and then here. So 4, so we're expecting 4 signals. All right. What about number 2? All right, you got 2 protons here, 2 here, 2 here, 3 here. And then what about the ring? What do you think?
You should have 1 hydrogen.
You got 4 different carbons on that ring, so potentially you have a total of 8 signals, potentially, with the hydrogens on the ring, each giving their own signal, and the 4 carbons in the chain giving their own signal. So we're going to say 8. 8 signals. Right? What about the number 3? What do you think?
Could it be 4?
Oh, 4.
Okay, so let's look at it. So this, you know, is going to give a signal. Yes, that's
Yes.
CH2.
Mm-hmm.
And then you got a CH right here that you know is going to give a signal. What about the CH3s? Are they equivalent? Remember we talked about that isopropyl type symbol?
Oh, yeah. They
So
should be equivalent.
Yeah, so that's going to be 1 signal, right? I'm gonna change the color and make them both the same color. So that's going to be 1
Well,
signal.
usually, if they bonded to the same carbon, they're equal.
Yeah.
Okay. That makes a lot of sense, Juanita.
Yeah, so, and remember, you can always test for that, right? You can pull off a hydrogen, stick another atom on in this place, and then the other hydrogen you want to compare to it, you do the same thing there, you compare the 2 structures. But normally when you have this type of isopropyl motif, where you have like a CH3 here and a CH3 here, those are going to be equivalent, right? Because there's a line of symmetry here. All right. Let me write that in. So those are going to be equivalent. Right. And then what about the OH? What do you think?
I'm not sure.
All right.
You said it depends sometimes, but you said that you would tell us.
Right.
If it's
Right.
yes or no.
So the OH may or may not show up. All right. So let's say that the OH is iffy. It depends. So you're going to see at least 3 signals for that. So I'm going to say 3, 4. 3, 4, 4 signals. All right. And what about the last one? What do you think? I mean, we've seen this one already. It just wasn't, it wasn't drawn like it is now, but we've seen it already. What do you think?
I would say 3 again, but the one on the left will be downfield.
Okay. All right. I'm with you. That's very encouraging to hear you say that. All right. So you're right. That's going to give me 3 signals. All right. So knowing that when we start looking at the spectra, we can kind of eliminate certain compounds based on the spectra. So let's see what we got. All right. So we're going to start with this first spectra right here. And first of all, let's read the question, because it gives us a couple of things to do. First, it says calculate the IHD, which we're not going to do. That's just the index of hydrogen deficiency or degrees of unsaturation. Tells you how many rings or how many double bonds are present. You can do it's fairly simple to do, but I don't want to have to rehash that because that's something that we learned in part 1. But if you want to see it, I can show you real quick, and that'll help. That also helps to eliminate certain structures, right? Because if the IHD is, well, let me just do it. All right, so you do that by H molecule minus H ref. I'm sorry, other way around. H ref minus H molecule over 2, right? H ref is going to be whatever the number of carbons is. So 2N, you might remember this from part 1, 2N plus 2, right? Where N is the number of carbons. So that's going to be 2 times 5. Got 5 carbons plus 2, that's 12. And then H molecule is what's here in the subscript. So that's 10. So when you plug that into the equation, it's 12 minus 10 over 2, which is 1. What that means is that there's 1 pi bond or 1 ring present. All right. And so we can rule out at least 2 of the structures, right? Because if you look up here, you got a ring and 3 pi bonds. So that doesn't match that, right? If you look here, you have no pi bonds. So you can rule that, or rings. So you can rule that out. So it's going to be between structure number 1 or structure number 4 for that particular spectrum. All right, so let me see if I can cut those. Let's see. I'm gonna have to erase all of this stuff here and see if I can cut them and paste them on the other page. Well, I can't cut it, but I can copy it. And then so I'm gonna paste that here. And then I'm gonna go back and grab the other one right quick. Uh-oh. How the heck did that happen? Okay, sorry about that. Okay, so now we got our two potential structures, right? And coincidentally, how many signals is number 1? Does number 1 give? We already said it, right?
Yeah, it was 4, I believe.
4 signals, all right?
Mhm.
So this is 4 signals. And then we said this one would give 3 signals. Right? Look at the spectrum and tell me how many signals you see. You have a signal here, here, That's just a zoom here and then here. Is that right? So which one of those two compounds is that spectrum gonna represent?
Number one.
The top one, right? It gives 4 signals. You see 4 signals. You see the numbers over the top of the signals. What are those numbers telling you? What's the term for that number? It's the integration, right? Is that right? Does anybody remember what integration
Mm-mm.
determines? No?
Mm-mm.
The integration, remember we said if you put a curve over the signal and took the area under the curve, the integration tells you how many hydrogens each signal represents.
Okay. So that's not splitting.
No, the splitting,
Oh wait, no, that's neighbors. That's neighbors.
yeah, the splitting is the number of lines each signal is broken up into.
Mm-hmm.
All right, so we know now which one this corresponds to, right? It can't be this one. That's out. Right, so it's got to be top one. So now let's match them up. Let's see if we can match them up. And then there's another part of that problem we're going to do with the infrared. I'm going to give you a little bit of a taste of infrared. And then over the weekend, I'll send you an overview of infrared. All right. So look at number one. We said it's 4 signals. So now let's match the signals up. What about this CH3 right here? Where do you think that's going to fall? And what would be the splitting pattern?
I would think it's the tall single one.
Mm-hmm. The singlet at
Mm-hmm.
2.1314, something like that. Why do you think it's a singlet? I agree with you 100%. But why is it a singlet?
Because it doesn't have any neighbors. So
No
then
neighbors, right?
yeah.
So we're gonna call this. We're gonna leave it red. What I'll do is I'll box it in red, right? And it's a singlet, and it's the CH3. And the reason it's at 2.1 something is because it's adjacent to that sp2 hybridized carbonyl carbon, right? That's why it's downfield like that. All right, what about this CH3 over here? Let's get those out of the way. What do you think? How many neighbors does it have?
One. Well, 2 neighbors, but
Yeah, there are 2 hydrogens on the carbon next door to it, right?
mm-hmm.
And this carbon right here, that's a CH2. So that CH3 has, let me get a highlighter, not a pencil. That CH3 that's boxed in has 2 neighbors to the left of it. So what is the signal going to be split into? So this going to,
3.
Good. So I'm going to write right here, singlet. So that's going to be a singlet. This is going to be a triplet. Is that right?
Mm-hmm.
Now the question is, which triplet is it? Because you got 2 triplets. How can you distinguish between the 2?
The upfield one.
Okay, you think it's going to be the one upfield. And I agree with you. And if you look at the upfield triplet, what's the integration?
3 as well.
3, right? And so if you see that, when you see that, and you compare it to the other triplet, which is integrating for how many?
2.
2, it can't be that triplet. See, the integration is going to tell you how many hydrogens that signal represents. So you know, okay, this is 3, the other one is 2, and the signal, the set of protons I'm looking at is for CH3, so it's got to be this one. So we're gonna box that in that purple. Yeah, we're gonna box it in purple. All right. Now, what about the CH2 right here? What do you think about that? That's a CH2. How many neighbors does it have?
5.
5 neighbors. Good. 3 on the right with the CH3. And then on the other side of it, there's a CH2 right here. So N for that set of protons, N is 5. N plus 1 is going to be 6. Right? How much will this signal integrate for?
It'll be 6.
Mm-mm.
Oh wait, integrate 2.
Yeah, 2. It'll be representative of 2 protons, and the signal is going to be split into 6
Yeah,
lines.
signal is 6. Yeah.
Yes. So you can see right here. I want to zoom in because this is easy. This is an easy one to pick out. Right? You can see that this is 1, 2, 3, 4, 5, 6 lines. Right? And that's showing up at 1.6. Right? And the integration is 2. So we'll box that in that color. Are y'all following? Anybody not following?
We're following.
All right. Let me know if it's moving too fast or if you're not catching something. Let me know.
Okay.
All right. What about the last signal? What do you think? It's a triplet. It's the one that I have highlighted. I'm gonna change the color though because I already have purple somewhere on here. So I'm gonna change the color of that. It's this one. Oh, that CH2 right there. How many neighbors does it have?
5 to 3.
2.
Hey, let's think about it. You got it's only on the carbon that's immediately adjacent, the one right next door. So on this carbon right here, you got 2 protons. Is that right? On the
Yes.
carbonyl carbon, you have no protons.
Oh, okay. We're looking at the blue one.
Yes.
Okay.
Right. So that blue box, that's a CH2 in there. Let me put the hydrogens in. Right. So that has to be a triplet because it has 2 neighbors to the right, none to the left. And the integration is 2. See that? That number over the peak, that's telling you how many protons that signal represents. All right. Any questions about that? Okay. Let's do one more part of this. So I said match the spectrum. We already did that. We walked it down, figured out the peaks, what's the splitting patterns, all that stuff. All right. Now it says on C, match an infrared stretch for at least 2 functional groups. All right. So we haven't technically done infrared, but I'm going to give you a kind of a crash course. And then after that, I will talk more about it in more detail. So this is an example of an infrared spectrum right here, right? All of the kind of stretches or peaks that you see pointed down, those are what we call, that's where infrared radiation is absorbed. Right? right? Anywhere you see a stretch, that means that that particular functional group actually absorb radiation in that range, right? One of the key factors about or key characteristics of infrared is that every functional group has its own place where it shows up. I'm gonna abbreviate functional group. I'm gonna say wave number. Right, so every functional group absorbs at a specific wave number. The wave numbers are down here on the x-axis. And I don't know if you can see that, but it's like from 0 to about 4,000. All right, so what I'm gonna do, instead of giving you a long speech about how it works, I can do that later. I can give you, based on the structure, we can talk about why we see what we see. So this is the structure of it's a ketone. All right. And so that's two major stretches in here that we're going to talk about, because the rest of the stuff is crap, right? You can't tell anything from it. All right. What the major stretches are going to be carbonyl stretch, which is this C double bond O. That's going to show up somewhere between, let me say 1650 to 1800 reciprocal centimeters. That's what the wave numbers down here is measured in reciprocal centimeters. That's 1 over the wavelength. All right. So that stretch is common, right? If you see a stretch, and it's a strong stretch too, right? Very strong stretch. So if you see a stretch that shows up between 1650 and 1800, and it's a strong stretch, most likely that's going to indicate the presence of a carbonyl. So this stretch right here, that is your carbonyl stretch. Oh, no, that's too dark, sorry. Worse. Right, that's your carbonyl stretch right there. Right. So what happens in infrared is you basically are bombarding this sample with a range of infrared frequencies or wavelengths. And as you bombard it, the only sample that, the only wavelength that matters is the wavelength that matches the frequency of that CO bond, because it's already stretching. Like we have this misconception about molecules that they're still, but they're not. There's always stretching and bending and wagging and all kinds of different molecular motions that are happening within that molecule. And so when the frequencies match, then that's when you're going to see that absorbance and you get those stretches that show up. All this stuff down here, this stuff is crap, right? Maybe except for the peak, the stretch at 1170, because that's the CO single bond stretch, but the rest of it, crap. So we can't tell anything from it. We can't tell a lot from it, right? The other important stretch in here is right here, right? This is, that was a pen and not a highlighter, sorry. Right here, right? That is your alkyl stretching. right? And you can see you got all these carbon-carbon single bonds and carbon-hydrogen single bonds. And so that alkyl stretching always shows up somewhere between, I'll say 2,800 and 3,000. And it always looks jagged like that, right? It's always a jagged, kind of raggedy looking stretch, but that stretch corresponds to those carbon-carbon single bonds and carbon-hydrogen single bonds stretching. All right, so those are your two main functional groups in this compound. And so those are the two main stretches that you're going to see in the infrared. And the key, again, infrared tells me about functional groups. So every functional group has a specific place where it's going to absorb that radiation and give you a stretch or give you a signal. All right, any questions about that? So I have a list of infrared stretches I'm going to send you, because there are there's some stretches that you have to know, like you should have memorized. The carbonyl stretch is one, the alkyl stretch, aromatics, alcohols, alkene stretches, all that stuff. So I'm gonna send that to you later on today. Anybody have any questions? No questions.
No.
Okay.
Just rewatch the video.
Ah.
Yeah,
I'll
I
just
might need the
watch
video. I'm gonna need the video. Then if I have questions, I'm
Right.
coming back.
Right.
So a video to reinforce what we just talked about.
Mm-hmm.
Okay. All right. Not the video in lieu of me showing up, because I can just start sending videos. I'm
No.
joking.
No, no, no,
I'm
no.
just joking.
No.
I'm just joking. I'm gonna send it today, and then you'll get like a better understanding of the theory. I didn't want to get too much into the theory because I know I didn't have time, but the theory behind it will make it make more sense. So I'll send that to you sometime this afternoon. All right. So I got to stop the share, and I hate that I have to cut this short.